And some solved problems for chapter 27. First, we have a metal that's radiating some red light. It's asking us how hot it is. So we're looking for a relationship between the temperature and the wavelength. So 2.9 times 10 to the minus 3. So we're looking for, here we have the peak temperature, peak wavelength. Here we have the temperature. Basic example of Wien's law, and it's a simple matter of solving for it. So 2.9 times 10 to the minus 3 divided by the wavelength, so 520 times 10 to the negative 9th, and we're going to end up with 5577 degrees Kelvin. And now, if you've ever driven down the road listening to your favorite radio station, wondering how much energy is in that electromagnetic wave, here's a quick calculation for it. So we have the frequency of our radio station. It's going to be 91.7 times 10 to the 6 hertz. That's the mega right there. And we have a very simple relationship between energy, Planck's constant, and frequency, where Planck's constant is simply 6.6 times 10 to the minus 34th. Frequency is going to be 91.7 times 10 to the 6 hertz. And we go ahead and we calculate this out. It's going to be 6.08 times 10 to the negative 26 joules. Very small number, not enough energy to knock you off your feet, but definitely enough energy to drive an electron in your car radio. In problem number 14, we're looking for the momentum of an X-ray. We know the wavelength, so I've gone ahead and converted that into SI. So momentum is going to be related to the wavelength simply by Planck constant. And so 6.6 times 10 to the negative 34th, once again, divided by the wavelength, 0.014 times 10 to the negative 9th. It's going to work out to a momentum of 4.7 times 10 to the negative 23rd kilogram meter per second, and again, going to be quite small. And lastly, problem number 56. Here we have a hydrogen atom. It's got an electron in the ground state, so kind of envision the positively charged nucleus, an electron in the closest possible orbit, and essentially we're going to have a photon. It's my little squiggle right here. Come in. It's going to knock that electron off, and it's going to give it some kinetic energy. So what we can kind of do is kind of picture this guy as a well. We'll say that the electron is just kind of hanging out in the bottom of the well. The deeper the well, the stronger the force. The more energy it's going to take to knock this electron first out of the well. So that's going to be what happens when we ionize it. Now we're also going to give it some kinetic energy, and so what we're kind of going to say is we're going to say that the energy of the photon, that's going to be be related to its frequency, which is going to be related to its wavelength, so hc divided by lambda. We've simply said that frequency is the speed of light divided by wavelength. That's going to be equal to, first, the energy to ionize, so that's going to be the energy right here to knock that electron out of the well, plus any kinetic energy that the electron's going to have. So here it has some kinetic energy. Now this is going to be hydrogen, so you go ahead and you say, well, how much energy does it take? Go ahead and look that up in the book. It's going to be 13.6 electron volts. Kinetic energy of the ejected electron is going to be 11.5 electron volts. And so go ahead and add these two guys together, and we're going to get 25.1 electron volts. And we can kind of say, well, I know that this guy right here, the number I have in my head, 6.6 times 10 to the minus 34th, that's going to be in joules. So I need to go ahead and convert electron volts to joules. I know that 1.6 times 10 to the negative 19th joules is going to be 1 electron volt. So go ahead and multiply these guys together, cancel out my electron volts, and I'm going to get 4.016 times 10 to the negative 18th joules. Now it's a simple matter for solving for wavelength. So we're going to say that the wavelength is going to be equal to hc divided by the energy, 4.016 times 10 to the negative 18th. So 6.6 times 10 to the negative 34 multiplied by 3 times 10 to the 8th. Divide all that by 4.016 times 10 to the negative 18th. we're going to end up with a wavelength of 4.93 times 10 to the negative 8th meters, or 49.3 nanometers. Now, the key thing to this one is to look for this word ionize, which says we're going to knock this electron totally away from this positive charge, and then so we're going to knock the electron out of the well. If it said that it excited it from the ground state to the first excited state, then we'd say, okay, ground state, first excited state, that's going to be the energy that it takes.